Okay, good morning. Let's continue with our class, and I hope to round up chemistry today so that we can finish the second part of my topic in due time. Since the video is on YouTube, I don't know why you are doing cloud recording. Anyway, so in the last class, we defined thermodynamics, internal energy, and their various characteristics and enthalpy. So we'll continue by looking at ways in which we calculate enthalpy change. So one way is calorimetry. So this can actually calculate both enthalpy and internal energy. Then we look at Hess's law and bond enthalpy. So let's pick them one at a time. Probably we spend 10 minutes on each one. So calorimetry is the science. So this is the science of measuring heat flow in a chemical or physical process. You know, when we're talking about chemical process, so that's chemical reactions, physical processes, those that don't change the substance. So when the substance or the instrument that is used is often called a calorimeter. It's very, very important in determining enthalpy changes, and it's also accurate, at least more accurate than the other two. The principle behind calorimetry is when you put two bodies together, when you put two objects together, the one that is hotter will transfer heat energy to the colder one. So there's the amount of heat lost from the hotter body is equal to the amount of heat gained in the hotter body, in the colder body. So I think the updated, okay, so this is the updated slide. That's calorimetry is the science. Apologies. So when you put two objects together, A and B, heat flows. So the amount of heat lost from the hotter body is equal to the amount of heat gained in the colder object. So that's the major principle, and it's the one that can help us to calculate the heat capacity, and it can also be related to the delta H of different processes. So let's see. Let me see any comments so far. Okay. So the body at a higher temperature releases heat, while the one at a lower temperature gains heat, and the amount magnitude is equal, just in opposite sign. The heat transfer is calculated by this equation. We already know what Q is. Q is the heat absorbed or heat released, depending on the object that you are looking at. Mass, N is the mass, and it's usually in grams, but it's good to convert it to kilograms. C is heat capacity. Heat capacity, we'll look at what that is in the next slide in a moment. And delta T is the change in temperature. So object one, principle, if we're going by this equation, so the principle means that the heat released is equal to the heat gained. So if we call this the heat released, so this will be the heat gained. See, T1 minus TF. T1 is the initial temperature of object one, and T2 is the initial temperature of object two. So we can carry it out at constant volume. The process can be carried out at constant volume or at constant temperature. When it's at constant volume, we are measuring internal energy, or sorry, more appropriately, we're measuring the change in internal energy. When it's at constant pressure, we're measuring the change in the enthalpy. So we are not measuring internal energy. So please correct the slides while you're going through them. We are measuring the change in internal energy or the change in enthalpy. So let's quickly run what is its capacity. I know you are familiar with it, but let's just go through it. So its capacity of any substance. So you define its capacity for a substance. It's a substance that we use in our systems. So the its capacity are people online yet? Please share the link online with your class. Okay, so people are already online. Don't go too far. What about bomb calorimeter? Don't go too far. So its capacity, when you're defining its capacity, whatever you are measuring, that thing has the ability to absorb it. So it's the substance is that defined as the amount of heat that's required to raise the mass. So that's the general definition for its capacity. In some cases, we prefer to use the specific heat capacity, which is it required to raise 1 gram by 1 kg. So its capacity is C. Let me expand this. Q over change in temperature. The specific heat is Q divided by mass divided by change in temperature. In chemistry, we like the molar heat capacity, which is the amount of heat required to raise 1 mole of a substance through 1 Kelvin. So by changing the temperature of 1 mole of a substance by 1 degree centigrade. A change in degree centigrade means it's the same thing as a change. Just a degree change in Kelvin is the same as a degree change in degree centigrade. Okay, so somebody is even asking that question. Yes, because of the relationship. What's the relationship between centigrade and temperature? So Kelvin is equal to what? Degree centigrade plus about 273. So since their relationship is plus 1 degree, so delta 1 in Kelvin is equivalent to a 1 degree change in degrees Celsius. But it is not the same. There's another unit that we encounter from time to time in temperature, which is the Fahrenheit. It is not the same as that. Yes, the link remains the same. So let's move on. There's a relationship between all these three. So this relationship, I just updated it this morning. It's not on your side, so please note that. So C, we have defined that as the heat capacity here. That's mass times the specific heat capacity. And so it will be equal to number of moles N times the molar heat capacity. Okay, just something to, so this is specific heat capacity of some substances. It seems that water has the capacity to retain heat. So when you're talking about heat capacity, just a little bit to divert a little bit. So if it is high, it means that the substance can hold on to heat for a long time. It's not a good conductor. If it's low, it cannot hold on. So the amount of heat that it can retain, it can hold on to at that point is not much, and it can easily give up heat. More often than not, the ones that have low heat capacity are better conductors of heat. Okay, so what I was about to say, usually in chemistry, whenever you hear heat capacity, 90% of the time, we're referring to the molar heat capacity. So if I interchange heat capacity and molar heat capacity, know that in both cases, I'm most likely referring to the molar heat capacity, unless it is specifically emphasized. Thank you. So we said that we can measure the heat change at constant pressure or at constant volume. They're slightly different. They measure different things, but we can consider them alike. So when you're measuring constant pressure, you call it constant pressure calorimetry. So this measures heat flow during a reaction at constant pressure. And the heat flow or the heat content or the change that you measure in that case is the change in enthalpy. Change in enthalpy. It is not change, it's not enthalpy, but change in enthalpy. For those of you that have tried to put two coffee cups together, you know, those styrofoam cups, and carried out a reaction in it. So that's a crude way of setting up a constant pressure calorimeter. And it's also a cheap way. From time to time, I think you will do that in next semester's lab experiments. For those of, in this constant, so this is two cups together. This is one cup, that's another cup. And your solution is inside that cup. So we put a stopper here so that you don't want escape of matter. So we call this one a constant pressure calorimeter. So this is a constant pressure calorimeter. Constant pressure calorimeter. The system is the reactant inside and the products within the solution, and the surrounding is the water. And of course, the calorimeter, because they can it can absorb its own heat. But one basic absorption is that this is perfectly insulated from the remaining part of the environment. Okay. All right. So when you mix the two solutions together, a reaction occurs. If it's an exothermic reaction, it releases heat, the water gains heat. If it's an endothermic reaction, the water loses heat, the solution temperature drops. That is, it flows from surroundings to system. We know what exothermic and endothermic reaction is all about. Any which way. So how do we calculate the heat of the reaction? The heat absorbed or released by the solution is, you see, that's the standard equation. So that equation is a must know. Q equals MC delta T. So the heat gained by the solution, or say that's the heat specific heat capacity, and M is the mass of the solution. Or if in a different place, you can talk about NCM. So this is CS delta T. So this will be number of moles, and that's the molar heat capacity. The relationship to the reaction is whatever heat that you supply, the heat of the solution that you get is the delta H of the reaction. So it can help us calculate the enthalpy of the reaction. I'm going to the next slide and okay. What's going on? Delta, okay. My tablet has taken over from me. So the Q reaction is that of the Q solution based on what we said of the principle that Q lost is equal to Q gained. So the system either gains or loses, and the surrounding either loses or gains, depending on the type of reaction it is. Then there's the one that we measure at constant volume. So the bomb calorimeter is used to measure internal energy, its change at a constant volume. I don't know, my apologies though. My tablet is the one that is controlling me now. I've told you, please stop putting unnecessary comments here. If you don't like somebody's, what does that mean? Previous slide. Ah, is it in all cases that M is molar mass? Or so I think I wrote so capital M is the small m is often mass. So it depends on how it is written. And also 920. Also, more often than not, it's going to be defined. So it's important that you follow what's described in the question. So, bomb calorimeter is often used to measure combustion reactions. I'm trying to expand this thing because it's looking small. But anytime I do it, the thing takes over from me. So the constant pressure calorimeter measures delta H, bomb measures delta U. So the bomb again is constant volume calorimeter. So it's so this is slightly different from your slide. So what it contains is the whole thing is called this is the bomb calorimeter. You have your sample system here. This is connected to an electric current that you ignite so that the reaction can take place. So, and your system is inside a sample cup. So there's a place where you pass oxygen through it, so that you can determine the amount of oxygen that is being used up as well. And everything is insulated. And you can monitor the amount of heat that has been absorbed. The system is the substance being burned. That's our system. And the surrounding, so system, and this is our surrounding, and everything is the universe. So the heat absorbed for the reaction is the heat capacity of the calorimeter times change in temperature. How do we determine the heat capacity of the calorimeter? It's often calibrated or standardized by burning substance, which we know the heat capacity inside the system. Once you burn that substance, you can determine the the capacity of the total calorimeter. Because again, the Q reaction will be equal to minus Q surrounding, which is that of the calorimeter. Let's work some examples. So to the person that asked about bomb calorimeter, I hope I've been able to answer your question. So let's work one or two examples because we have to finish this topic today. A metal weighing 4.2 gram, 4.82 gram. So mass 4.82 gram was heated to, so the final temperature is 115.0 degrees and placed in, so no, that's the initial temperature for the metal. It was now placed in 30 ml of water, volume of water 35 ml. The metal and water were allowed to come to equilibrium and the temperature to an equilibrium temperature, which is 34.5. So that's the final temperature, 34.5. Calculate the specific heat capacity of the metal, considering that the specific heat capacity of water is this and mass of water is that. Okay, so the temperature of water rose from 28 degrees to 34 degrees. So this is initial of water to that. So which means the heat absorbed by water is given by, so why are we saying heat absorbed? Because the temperature is rising. So mass of water, the heat absorbed by water will be mass of water times specific heat capacity of water times change in the temperature that the water experienced. So mass of water we're not given explicitly, but we're given the volume of the water that was used, and we're given the density of water. And we know that mass is volume times density. So we can calculate the mass of water. Substituting the values, we get, so if you substitute those values, you get the heat absorbed by water to be equal to that. Principle of calorimetry, heat lost is equal to heat gained. So this is Q water. So, and that will be Q metal. And we have calculated Q water to be 849. So let's calculate the specific heat capacity of the metal then. It will be equal in sign, the amount of the heat, it will be equal in magnitude, opposite in sign to that of water. So that means Q metal, same formula, Q is MC delta T. Okay. Any question? So if we slot in the values, the mass of metal was given in the question. We can calculate the specific heat capacity of the metal, and it's given as that. Okay, no question. I'm leaving the slide. Another question, in an experiment, 25 ml of 1 molar HCl is added to 25 ml of 1 molar NaOH in a foam cup calorimeter. So that is constant pressure. If the reaction occurs, reaction occurs and the temperature rises, calculate the enthalpy change. See, it's a constant pressure, so we are calculating enthalpy change. So we're given, assume the density of the solutions to be 1 gram per mil. And this is often assumed because we're working in water, and the more often than not, it's a dilute solution. So it's still density of water that usually presides. So we know that the specific heat capacity of water is this. The final volume will be the volume of HCl plus that of NaOH. That's the volume of water. So what are we to determine? We are to determine delta H. Okay, so the volume and density can be used to find the mass after mixing. How? Because the heat that the heat absorbed is equal to the delta H. And since it's a calorimetry reaction, we know that the Q of the system is equal to the Q of the surrounding. The Q of the system is a reaction taking place, and the surrounding is the water and the cup. Okay, so the Q of the surrounding, which is that of the water plus specific heat capacity at, so this P is at constant pressure. You can make it S. Mass is volume times density, so we have 50 grams. C is 4.18. Delta T is 7.0 grams. So substituting all that, we arrive at our delta H being equal to 1463 joules. Five, no question. Okay, so the next concept in measuring delta H, Hess's law. According to Hess's law, is it my system that is? When you carry out a reaction in several steps, the total delta H of all the individual steps, if you sum up them all together, is equal to the total delta H of the net reaction. The overall enthalpy change for a reaction that is carried out in a series of steps is equal to the enthalpy change of all the individual steps. What are we trying to say? So, for example, this is a reaction A going to B. A is the reactant, B is the product. It is possible. Why are you putting minus? I was waiting for question to be asked. So I want to believe you're asking about the previous slide. So Q gained, Q of the reaction is equal to minus Q of the system. Because one gains, the other loses. So consider a reaction A, reactant, going to B, product. This is reactant, this is product. So A can be directly converted to B, one-step reaction. We call such reactions one-step reaction. Or if, for example, you add a catalyst because the what you might call it, the activation energy from going directly to A to B might be too large. So you go through an intermediate. So you go through an intermediate called C to B. So C is an intermediate because it's not the final product. It's a stop along the way to the end of the reaction. And for you, the change in enthalpy for C, A to C is delta H2. The change in enthalpy for C to B is delta H3. It's also possible that you go through the D2 intermediates. So what Hess's law is saying that now this A that can go from A to B, or can also go from A to C, then finally to B, or from A to D, D to E, then finally to E. The total energy, the total enthalpy of directly going from A to B is delta H1. So what Hess's law is saying is that this delta H1 is equal to the sum of delta H2 plus delta H3. And in another step, it is also equal to H4 plus H5 plus H6. So let's read it again. The overall enthalpy change for a reaction that is carried out in a series of steps is equal to the enthalpy change of all the sum of all the enthalpy change of all the individual steps. So the enthalpy change is the same regardless of the number of steps taken. So if you're taking it one step, that one step is equal to the enthalpy change of all the one steps combined together. The reason is because enthalpy is a state function. So I've repeated the Hess's law. So there's a diagram here just to emphasize it. Carbon dioxide, methane, the combustion of methane can go through initial conversion to carbon monoxide before final conversion to carbon dioxide. The delta H for the whole reaction is equal to the delta H of individual steps. Let's look at an example to buttress this point. So we're given C plus O2 to give that, and CO plus, so this is our reaction. Combustion of carbon to carbon dioxide, and then combustion of carbon monoxide to carbon dioxide. We are to determine the enthalpy change for this reaction. Remember, we are looking at ways that we calculate enthalpy change because absolute enthalpies are difficult to measure. Is there a finite number of steps to be taken, or is it based? It is based on the reaction. It is based on the reaction and the type of reaction. So there are some reactions that go up in one step. There are some that go in several steps. Okay, so let's see. This is the equation that we are to determine the enthalpy change. So when you're given such an equation and you're given other expressions, the ideal thing is to compare it. When you're trying to compare it, the ones that you know, you want to align it with the unknown one. So this is our unknown. This is our unknown. Unknown. And I've been writing beautifully before. This is our known reactions. Unknown reaction delta H. So you want this these known reactions, you want to arrange them in such a way that their reactants align with the reactants of the unknown, and their products align with the products of the unknown, of the known, of the unknown. So let's look at equation 1. This is labeled equation 1. If we look at it with an unknown reaction, maybe we can call that equation 3. Carbon is on the reactant side, carbon is on the reactant side. It's 1 mole of carbon, so we are fine. So we can leave it as it is. Equation 1, we leave it as it is. Then equation 2, carbon monoxide is on the reactant side, and we want it for the reaction we are trying to determine, it is on the product side. So we are going to move carbon monoxide to the product side. And in moving it to the product side, the delta H changes sign. It is negative here. It is now positive here. The delta H changes sign. One other thing that's also noted is when you moved it, you have 2 moles of carbon monoxide here, but you have 1 mole of carbon monoxide there. So we're going to divide it by 2. So if we divide this by 2, we get CO2 to CO plus half O2. And since we are dividing it by 2, we also divide 68, the delta H, by 2. One of the properties of enthalpy, it is an extensive property, meaning it depends on the amount of substance that are present. That's what I just said. I'm dividing it by 2 because H is an extensive property. It depends on the amount of substance in there. We have divided the whole reaction by 2. So we are going to divide the delta H by 2 as well. So we compare now C, so equation, so let me write equation 1 here again. So that is C plus, again, let's put plus O2 gas going to CO2 gas. So that's still our equation 1. So if we add equation 1 to this equation, let me try to see if I can write it here. So carbon solid plus O2 gas going to CO2 gas delta H is equal to minus 94 kcal. So if we add this, bringing everything together, so carbon, let me write the whole expression somewhere here. Carbon, so I'm going to discard the state of matter for now, plus CO2 plus O2 going to CO plus half O2 plus CO2. So I've written out everything out. It's the same thing that we have here. So CO2, 1 mole of CO2 cancels out 1 mole of CO2 on both sides. So we have carbon. There's oxygen here. There's half oxygen here. So we have excess. So we are left with half oxygen on the reactant side. So we have our reaction. If we compare this reaction to what we are trying to determine, that's what we have. Now, since we have added the reactions together, we are going to add their delta H together as well. So the answer for our reaction is minus 26. So which reaction is confusing us now? How did you get 68? You minus, you mainly used from 91. You understand? Please, let's follow along. Let's follow along. We don't have enough time. So which reaction, this equation, do I have a white? Can I use whiteboard? Let me go over the reaction again. Play. So let's go through the reaction again. So equation 1, my writing is not going to be as fine as the things that I typed there. So we have C. So I'm going to discard the state of matter for now. Our delta H equals minus 94. Equation 2, 2CO2 plus O2 going to 2CO to CO2, delta H is minus 136. And we are looking to calculate C plus half going to CO. We don't know the delta H of the reaction. So pay attention. So let's compare equation 1 to equation 2. Carbon, that's fine. So that's the key thing here. So that one stays. Equation 2, the carbon monoxide is on the product side. Because the carbon monoxide is on the reactant side, we want to align with the unknown. So because we want to align, we're going to reverse that. If you reverse this, you have 2CO2 going to 2CO plus O2. Remember, when you are reversing, you are putting whatchamacallit, you're putting the reactants on the product side and putting the product on the reactant side. So why did I reverse? I'm reversing because I am trying to make this equation such that its product will be in this, will have the same product, will be on the same, its product will be on the same side as the product of the one that we are trying to determine, because we are using it to determine equation 3. Okay, so because I have reversed it, the delta H will now be reversed. It will now be plus 136. Okay, yes. Now, however, it is 1 mole of carbon monoxide here, but we have 2 moles of carbon monoxide there. So again, I will now divide this equation, which I now call equation 4. I'm going to divide it by 2. So once you divide it by 2, that will be CO2 divided by 2. 2 goes off, going to CO, 2 goes off, plus half, since this is 1 over 2, O2. And once I do that, delta H also is divided by 2. That gives us positive 68. So once you get positive 68, so let's compare this to our reaction. So half O2, we're fine with that now. Sorry, so CO, you know, the main thing here is carbon going to carbon monoxide. So we want to eliminate CO2 because it's not in the net reaction. What's the time? 9:49. And we want to maintain only carbon monoxide, and carbon dioxide, and the oxygen in the reaction. Sorry. So now let's now look at equation 1 again. C plus O2 going to CO2. Comparing, we see that if you, this is CO2 is on the product side here, CO2 is on the reactant side here. They're both 1, you can eliminate it. So you have to really look at it. I'm not going to be able to work the second example at this rate. I'm going to go straight to bond enthalpies. Wow. Okay. So where was I? So this still remains minus 94. So now I'm getting the question. How did I get minus 9? Maybe this is minus 94 in the question. Okay, so let's see. If I add these two equations together, CO2 cancels CO2, I'm left with C plus O2 to CO. So let me go back now so that I can show. Ooh la la. People are not trying to understand. I'm not trying to listen. I can't believe it's not ready one up. So if you add those two together, you have minus 26. So take time and go through it again. I cannot spend the whole of today with this example. Let's look at enthalpy of formation. We're supposed to talk about 3 things today. We have only talked about 1. Enthalpy of formation. Goodness gracious. The enthalpy of formation is another way you can use to calculate standard enthalpies of reaction. So why? The enthalpy of formation, it refers to the change in enthalpy when 1 mole of a compound is formed from its elements in their standard state. So you take the elements, for example, water, the elements hydrogen, and oxygen. So when we're talking about reference states, depending on the textbook that you pick, it can be they you can refer to it as standard states. In physical chemistry, is often referred to as a reference state. So that standard state for the element is the most stable form at a specified temperature. More often than not, the temperature is often around 25 degrees centigrade. Thank you for understanding better. More often than not, the temperature is around 25 degrees centigrade or 29 Kelvin. And the pressure is 1 atmosphere, or in some other books, you can see 1 bar. 1 bar. Usually, so that's probably temperature at a certain height above sea level. Because there are elements that have different forms. You can have carbon existing in diamond, several allotropes. Graphite is the most stable form. Phosphorus exists as white phosphorus, pink phosphorus, and all whatnot. White phosphorus is the most stable form. However, people prefer to use pink phosphorus because it is the most ubiquitous. That metric number is not even correct. Then sulfur also exists in several, in several allotropes. Then you have these our elements, for example, oxygen, hydrogen, that exist in their molecular form, and that molecular form is the most stable form at those conditions. It is not H or oxygen. Mercury is liquid, noble gases. So more often than not, what does ubiquitous mean? Ubiquitous means it is most available, it is abundant, it is found everywhere. So when we're saying the enthalpy of formation of a substance, so this is ethanol. So from its reference element in their standard state. So this is an equation that represents the formation of ethanol from, so we're looking at carbon, hydrogen, oxygen, and hydrogen. So carbon, hydrogen, and oxygen. This is the reference state for oxygen, the reference state for hydrogen, and the reference state for carbon, not diamond. Somebody asks, is it important to write states of matter? Absolutely, it is very, very important. And this is for glucose, H, oxygen. This is for water. So it is for the formation of 1 mole of that compound. It's for the formation of 1 mole of that compound. Which property makes enthalpy behave as it does? So the fact that it's a state property, state function, and it's extensive property. So the standard enthalpy of formation of any element in its standard form is 0, because you cannot form it from anything. Let me explain this a little bit in the next slide. So this is another repeated slide. So look at bromine liquid here. It is 0. So if you want to form gaseous liquid from bromine liquid, you have to have some energy. So the standard in their reference states, it's 0, 0, 0, 0. Iodine is solid. So these values that we're looking at may be used to calculate the delta H for any chemical reaction once we know the standard enthalpy for the reaction. So based on the property of Hess law, so how do you calculate it? So you look for the enthalpy of formation of the products, sum it up together. Remember to multiply it by their stoichiometric nature. Why? it is an extensive property. Enthalpy is an extensive property. And then look for that of the reactants, sum it up together, while also minding the stoichiometric coefficients of the reactants, and then you subtract it from that of the product. So for example, so that's an equation for you to know. So for example, so let's look at an example. So calculate the delta H for the reaction of that. We're given 1, 2, 3. So if you critically look at these reactions, so when I say extensive property, it depends on the amount of substance present. So if you have 1 mole and you have 2 moles, the delta H will be different. So there are some things, temperature does not depend on the amount. So it's the temperature of 50 mils of water at certain condition is the same temperature. It doesn't matter. It's not dependent on the amount. So that's what. So temperature is not intensive. Sorry, temperature is not extensive. It is intensive. So looking at this, you would realize it is their heat of formation, and we have NH3. So simple to calculate. The delta H of reaction will simply be the delta H of formation of the product minus the sum of delta H of formation of the reactant. So slot in the values and you get what you're looking for. Okay. Another example here. So we're to calculate the enthalpy of formation of this reaction. What you will do, you're going to be given a table. So in the exam, you are not required to memorize the heat of formation of everything that exists in the world. So you'll be given, so carbon dioxide is somewhere, where is it? I can't find it. This is carbon dioxide. And this is carbon monoxide. And that is, where is oxygen? This is oxygen. So slot it in and we get our delta H of formation of reaction. So there have been, the last one that I want to talk about today, the last thing that it's actually not the last thing that I want to talk about today, but it looks like the last thing. And you'll probably be required to read the rest of the notes. Bond enthalpy can also be used to calculate delta H of reaction. So just like delta H of formation, the bond enthalpies have also been calculated for several bonds and has been recorded. So the bond enthalpy is defined as the energy required to break 1 mole of a bond in a molecule. So you have H2O. So H2O has OH bond. So the amount of energy required to break this OH bond is the bond enthalpy of the come on. Sorry, is the bond enthalpy for that reaction. So bond breaking is endothermic. Endothermic in that it requires energy, but bond formation is exothermic. So this is the more appropriate. So the bond enthalpy is the energy required to break 1 mole. So you're going to break 1 mole. So with a unit of kilojoules per mole. Please update. So it's not as detailed like this in the slide that you have. So please update. So for example, bond forming is always exothermic, but bond breaking is endothermic. Now, the key thing that I want to talk about here is the average bond enthalpy. That's the bond enthalpy that we have defined, often given the symbol D or BDE, depends on the environment. So I mentioned OH the other time. So this is OH in water. You can also have OH, COH in, this is methanol. You can also have OH in hydrogen peroxide. So they vary slightly. All these OH vary slightly. But we now have the average bond enthalpy. The average bond enthalpy, I don't know why I've duplicated almost all my slides. So the average bond enthalpy is the average of several bond dissociation enthalpies. So it's the average amount required to break 1 mole of a specific bond in a molecule, resulting in the separation. So like the example that I gave, the average of OH will be average of several OH in different bonds. So for a bond like this, the average will be a molecule like CH4, which we usually draw like this, even though that's not what it looks like. So this will be really different, but then we now take the average of all of them together. So the bond enthalpy varies with environment. See, CH bond in here, here, you can see the vary. Here is 380, here is 430. So this is another place, another CH bond here now. 435, 453, 452, 339. So, but the average of these bonds are often reported in our handbook. So these are several average bond enthalpies. And the average bond enthalpy that is given is the one that is the dissociation. So you see it given as positive. So this is for some multiple bonds. This is for single bonds. How is it related to delta H of a reaction? The delta H of reaction is equal to the summation of bonds, the bond dissociation of bond broken, minus the summation of the bonds dissociation of the bonds formed. So let's work an example on that. Okay. The reaction of hydrogen with chlorine gas produces hydrogen chloride. So H2 plus Cl goes to HCl times 2. Calculate the enthalpy reaction for the reaction, enthalpy change for the reaction using bond enthalpies. So one thing that it's on that slide, but I think I did not mention it. When you're using bond enthalpies, you are only getting an estimate of delta H. And the reason why you are getting an estimate of delta H is because you are using average of several bonds. And that matters to the particular bond that you are thinking about. Some of you are writing your names without your matric number. That's not your complete information. So the thing is, when you have a reaction like that, it is important that you identify the bonds broken. The bonds broken are those of the reactants. So our H plus Cl going to 2 of HCl. So we were given the bond dissociation of all the types of bonds that are present. So total energy of bonds broken is equal to that. Bonds, identify bonds formed. The bonds formed in the product is hydrogen chloride bond. And there's two of them. So we're going to multiply that by 2. 431 is given in the question. Okay. Then we apply the formula. Bonds broken minus bond formed. So the enthalpy for the reaction is equal to that. Question. So there are other examples there. So from what I gathered today, the one that is really confusing you is the Hess's law. Maybe I'll share additional examples, written examples for you. So this other one seems to be straightforward. There are many other examples in your slide for that. How did I get 431? Where did I get 431? Four 31 is given now. It's given in the question. One application of energies that we see around is calculating energy in food. Energy in food, that's the amount of energy released when the body consumes food. The body consumes food and metabolizes food. So you've seen a lot of food. When you pick up your label, they say this is chemical, 100 gram contains this and that and that and that. So the major sources of energy in food, I'm going to go through this very quickly. Carbohydrates, that gives you 17 kilojoules per gram. Then you have fats, it gives you 13. So you metabolize 38. Can you rewind? I couldn't help during the chemical. 38 kilojoules per gram. So so you have a carbohydrate being the primary source of food. This one, the fat undergoes combustion. They are ideal energy storage. So that's why we store them in our bodies. Another one is protein. Protein is not really, so what it does is it has structural role. So average energy is 17 kilojoules per gram. No, that's not correct. Anyway, so we have alcohol. The food value in alcohol is 29 point, but it's not a good food value. And then we have this one, but the major ones that I'm looking at are the protein. So this, you can read them on your own. What I want to mention here is that how do we measure food in energy? We use bomb calorimetry. Bomb calorimetry, that is reaction inside the closed container for at constant energy. So this is how is this how do I want to say it? Mostly converted to glucose. So it's from glucose energy that we get this. So the amount of Um, now I'm rushing because I'm out of time. We'll send worked examples, but the note is quite explanatory on this side. Anyway, these are the different kind of food items, and this is our own food item. Oh, per 100 grams. Then there's that of fuel too. Fuel substances that contain stored energy and can be released. Yeah, you have the slides. I've shared the slides before. Please ask your class reps. I have shared a link to the slides. I will share the link again, but I've shared the link to the slide before. If we have enough, I'm supposed to meet you one more time, and we are going through a different topic. So you can decide amongst yourself whether you want us to start very early on Friday. Because the next time I'm seeing you is on Friday. No, yes. So fuel contain chemical energy. That energy is released during a chemical reaction, typically combustion. There are some that you have nuclear change, or the one that hydrogen undergoes in a fuel cell where you produce hydrogen. The energy released can be transferred or into electricity and some other thing. What I want to mention here, the combustion of fuel, which is the most one that we use. So this is one of the practical uses of thermochemistry, thermodynamics. The combustion of fuel gives you carbon dioxide and water. So carbon is converted to carbon dioxide, hydrogen is converted to water. These two reactions, they have large negative enthalpies of formation, large delta H, meaning that they release large amounts of energy. So people, when we're looking at fuel, the one that has a higher carbon content and higher hydrogen content gives you a higher energy value. And that is why crude is of serious importance nowadays. Then that energy value is often measured in this. There are several types of fuels. Sorry. Those of us in petroleum engineering, so you can measure it in megajoules, in kilojoules, or in British thermal units. There are different types of fuels, the fossil fuels, the natural gas. So most of these ones, they contain carbon, hydrogen, and some other stuff. The higher the carbon and hydrogen content, the better the fuel. Once you have some other things, it reduces the energy conversion because delta H is lower. So there's a slide there that shows you the different types of fuel that we have. Other energy sources that thermodynamics looks into, the nuclear energy. Then you have some we've looked at the non-renewable energy, which is the fossil and the nuclear. So nuclear energy is energy from the atomic nucleus, whether it's fission or it is fusion. However, nuclear energy is only used very, very rarely because it generates a lot of radioactive waste. The fossil fuel, the major challenge with that is um, what do you call it? Environmental pollution. Then the non-renewable energy sources are the solar energy, wind energy, the geothermal energy, the water energy, that's hydroelectric, and the biomass energy. The CNG gas that is being used to power vehicles is, yes, it is from crude oil. It is a fraction of the crude oil. So by higher energy value, do you mean, so I mean, yes, it gives a more negative enthalpy. Negative enthalpy means that you are generating energy. Positive enthalpy means you are taking more energy. So I've mentioned solar energy. So this explains it more. Solar energy can be converted to storage, another area of active research for those of you that want to go into research. I'm still surprised that you are asking for the slide. I'll share it again, but I've shared the slide with you before. All right, so that concludes our class. Okay, there's an example here. Calculate molar mass for, sorry, we comparing fuel values, methane, octane, and glucose, which has higher energy per gram. From delta H of combustion, methane gives 89.91 kilojoules. Octane gives 570 kilojoules. Glucose gives 5,470 rather. Okay, so it looks like this gives a lot, but when you compare it to the mass, we realize that methane gives the highest energy per gram, 55.48. And you see, it's one reason why one of the things that has been looked at now, people converting solid waste, defecated waste, to gas for cooking because it contains a higher level of methane, a high level of methane gas. So there are some questions at the end of the slides too. Any question? You said you want the slide. I'll share the slide again, but please ask your class reps. On the class reps group, I have shared the slide before. If you want, if you are willing to, I can go through the Hess's law again. So we will communicate with you. No, for those of you that want to stay, if you don't want, that's fine. Just the S law, because I realized that's the one that confused you the most. How is the delta H of hydrocarbon? Can somebody help me answer favor, Saka? How is the enthalpy of hydrocarbons obtained? Let me see if anybody was paying attention. The question is, how is the delta H of hydrocarbons obtained? No, it's a question on the chat box, so you can see it there. How is the delta H of hydrocarbons gotten? I don't like that word, gotten. I like obtained better. Thank you, Isaac. It's obtained by combustion, which is carried out in the bomb calorimeter. So, okay, so the standard enthalpies are used as estimates. So, thank you. So, what does favor? What don't you understand? I've told you I don't understand is not a question. So let us know what you understand, and then we'll go from what you understand to what you don't understand. Thank you, Rina Okefe. Finding the energy by its molecular mass. Okay, so the question that the person asked is, for those of you on YouTube, the question the person asked is, how do you obtain the delta H of hydrocarbons? So you obtain it by combusting it in the bomb calorimeter. The bomb calorimeter, when you are using a bomb calorimeter, you supply it for a certain period of time, and you can calculate that it that you supplied by current, voltage times time. So you see, there are several ways in which we convert energy from one form to another. That can be related to the heat of the calorimeter, which can be related to the heat of the reaction. Anyway, so let's move on away from that. This is an example, another example on Hess's law. So we are given this reaction, NO2 plus 13.5 to NO plus half O2. So this example, in this reaction, this is another thermochemical equation in which the heat is written with the reaction. So meaning that I can write this equation as NO2 going to NO plus half O2, and my delta H will now be minus 13.5. Now I'm solving the question on this side. That's why I'm not writing it. I'm going to solve it in two different ways. So similarly, this one is 2NO going to N2 plus O2, and delta H is equal to, sorry, delta H is plus 13.5 is on the reactant side. I apologize for that. Delta H is minus 43. And for the third one, N2 plus O2 going to N2O4, delta H is on the reactant side is minus 2 kcal per mole. Again, I am not writing the state of matter and units just for clarity purposes. So we are to find the enthalpy change for N2O4 going to 2NO2. Are we together? So let's look at this. N2O4, 2NO2. We cannot change this one. We are going to only compare every other thing to it. So this reaction, NO2, if we compare one with this, we will see that NO2 is on the reactant side here. It is on the product side here. Again, other than it being on the product side, it is 2 here, it is 1 here. So what that means is that, what do you think we will do to equation 1? Does anybody have something to that? To equation 1, we will probably bring NO2 to the product side. If we bring NO2 to the product side, it means that we are reversing the equation. Thank you. Let me see if that's the first thing that we need in the note. So it means that we are reversing the equation. Now let's look at equation 2, NO plus N2 plus O2. Now, if you look at that, it does not exist exactly. It does not exist in this. Nothing here exists here. So there must be a reason why we're given. So, but let's move on. You know, when you have plenty things, you have to look at what you need immediately first, and then you move on to the next. So if you look at N2 plus O2, this is energy. Then we have N2O4. It's on the product side here, but we want to bring it to the reactant side. It means we will also reverse equation 3. We are not going to multiply or divide it because it is 1, 1. There's nothing. So our new equations, know that the enthalpies are included. Our new equations now will be NO. So I've reversed equation 1 here. Reversed equation 1. Here, I have reversed equation 2. Equation 2 here. To reversed equation 3. Okay, I want to believe we are still following since there is no comment so far. So if you are talking about this place, I have brought it to the product side. In chemical reaction, we do not use, in chemical reaction equations, we don't use the negative sign. So the other way I can write this is NO plus half O2 going to NO2 and delta H now. Here it was positive 13.5, so it is now minus 13.5. And we have added it to the product side. Okay, thank you for those of you that have responded. Okay, so there is one more thing that is missing. I said it before. It is 2NO2 here, but it is 1NO2 there. In that case, we need to multiply this one by 2. That is only when we have that. So we are multiplying it. Please, Ma, why did you reverse the second equation since we are not using it? Did I reverse it? No, I did not say we are not using it. I didn't say we are not using it. I said, let's hold on for now. I'll get back to it soon. I'll get to it soon. So let's multiply this one by 2. Once we multiply it by 2, we also multiply the energy by 2. So again, so this is 2NO plus O2 to give 2NO2, and delta H is now minus 27, which is equal to 2 times 13.5. Fantastic. So why did I bring equation 2 here? I'll reverse it. Because if you look at those equations, now this one has NO, but the final equation does not have NO. The third equation has N2, but the final equation does not have N2, and it also has O2. However, equation 2 has both N2 and O2. So, and it also has NO. So it can help us to eliminate these ones that we do not need. On the reason why it was reversed, it's because we need to eliminate N2 from this product side and NO from the reactant side. So our equations are set. What we need now to do is to combine all the equations together. So when we are combining all the equations together, so the equations that we are combining now is equation 5, 6, and 7. Because we have this equation 7 is equation 4 that has been reversed. So the big one that scared the other person the other time So putting all the equations together. So this is equation 5, equation 6. Am I correct? No, so this is one is equation 6. This is equation 5. This is equation 7. Okay. I thought if the heat is on the reactant side, it gains heat. That is in the first equation. So if I understand you correctly, you're talking about the first equation written at Faith. Faith is on YouTube. Yes, the system is gaining heat. And that's why when I wrote it here, delta H, when I wrote it in the other way, let me clear it. Delta H is equal to positive 13.5. So if you sum this all up, now moving on, if you sum this all up, we get that equation, N2O4 plus 2NO2. Or you can write N2O4 going to 2NO2, and delta H is positive 14.0 kcal per mole. Are we together now? Or you want us to work that first example? But I want to show you this one in a different way too. Okay, no more question. If you want to put it in a diagram form, these are the equations that were given. So question is, how is the sum? How did you get 14? Let me go back to that slide. So you have 43 here, you have 27, and then you have 2. Again, how do I write it? So if you want to write the equation on the side, so this would delta H, let me put delta H in one column here. This would be minus 27. This is plus 43. And this one is minus 2. If you sum up everything together, add every, so that would be minus 27 plus 43 minus 2. You should get 14. So you have more energy on the side. Okay, so that's the way you generally solve for those people that like looking at diagram. Oh, come on. For those people that like looking at diagram, how did I get minus 2? How is it minus 2? Minus 2 in the sense that it is exothermic, is on the product side. So we are looking for the enthalpy of this reaction. We're given, I'm not looking at the same reaction. We're given this, and we're also given this. I think I'm going to confuse you more. So if this one is confusing, please, if this one is confusing, stick to the other one. You don't have to use anything. I'm just showing it in a different way for the people that like drawings. So this is what we're given, NO2, and that. We don't know what that is. But what we know is that when N2, O2 goes to N2O4, when N2 and O2, so from this reaction, if you add N2 plus 2O2, if you add N2 plus 2O2, you require 2 kcal per mole. So going here is a 2 kcal per mole, meaning that if you are going in the reverse reaction, it will be negative. We also know that N2 plus O2 going to 2NO plus O2 is 43 kcal per mole. And the last one is NO2 going to NO plus half O2 is 13.5. Well, since it's 2, so that will be so, which means this other way goes there. We're told to find X. So X will be, this is S's law in diagram. Now I'm going to answer your question in a minute. S's law in a diagram, N2O4 going to in one step. If it goes through several steps, you add everything together. So which is X will be equal to -2 plus 43 minus 2 times. So let me look at the questions. Does that mean that while writing a reaction, when enthalpy is written on the reaction, the sign doesn't matter? Thank you for answering that, Faith. The sign matters. If you're in the last class, there are 2 ways you can write thermochemical equations. You can write your delta H outside of the equation, and you would use the sign. But when you are writing delta H in the equation, you do not use negative sign in chemical equations. It is always positive. So if it's endothermic, you put it on the reactant side. If it's exothermic, you put it on the product side. Ma, was the 3 reactions added together to get the final reaction? Yes, it was. Because the middle one helped us to eliminate some other reactants or some other species that were not in the next reaction. Okay, so on Saturday, on Friday, we are going to talk about the second law of thermodynamics. That slide I will share with you, hopefully, before the class that day. Any other question? So we spent an hour and a half. Any other question? All right. Let's see. No more questions. Five, 4, 3, 2, 1. You're not serious. How can S's, so it's not a matter of whether S law is applying to fuel, it's applying to whatever you want to use it for. Are we allowed to come to your office? Where it's convocation, you are allowed to come to my office. Yes, you are allowed to come. You'll see me on Thursdays. I'm not giving you all my days. So for now, Thursdays and Wednesdays. I have recommended this textbook. Ask your class rep to always share what is shared with them. Okay. My 5 for I delayed that 5 because of those on YouTube, so I can now. My name is Dr. Whenu. How can I get to your office? You walk or you take a bicycle. Room 14, is that 147 or 148? Okay. Have a lovely convocation rice week.